In this video, we'll be looking at the flexural analysis of reinforced concrete beams. Reinforced concrete beam consists of reinforcing steel and concrete. Hence, we have to know the stress-strain performance of both concrete and steel as well. So if we look into the stress-strain curve for concrete, it looks like this, as we know. The stress-strain curve of concrete is linear in the beginning, and then it will start to become non-linear, and finally the concrete will crush when the strain in the concrete reaches 0.003. Epsilon Cu is the crushing strain in the concrete, and the maximum compressive strength of concrete is denoted as Fc dash. Different code gives the crushing strain of concrete slightly different. Australian Standard AS3600 takes epsilon Cu, the crushing strain of concrete, as 0.003, whereas the American Concrete Institute ACI code gives epsilon Cu as 0.004, and the European code gives epsilon Cu as 0.0035. But for this course, we will take epsilon Cu as 0.003. At that point, the concrete will crush in compression. Now, if we look into the stress-strain curve for steel, we know that the stress-strain curve for steel will be bilinear as shown here. Here we are ignoring the strain hardening part here because we do not know exactly where the strain hardening starts, and we cannot rely on the strength gain due to strain hardening as well. So we will be treating the steel as bilinear stress-strain curve for reinforced concrete design purpose. And so the important parameters for steel are the yield strength, FSY, and the corresponding strain in steel is called as yield strain. For the steel available in Australia, FSY, or the yield strength of steel, is 500 megapascal. And we know that the Young's modulus of steel is 200,000 megapascal. So with that, we can compute the yield strain at the point where the steel will start to yield. Now, epsilon SY, the yield strain, can be computed using Hooke's formula, Hooke's law, and that is given by FSY, the yield strength of steel, divided by the Young's modulus epsilon ES. Now, FSY is 500 megapascal, that's the steel we get in Australia, divided by the Young's modulus ES is 200,000 megapascal. Now that gives us the yield strain in steel as 0.0025. This is the point where the steel will start to yield. Now, to look into the analysis of reinforced concrete beam, we will first consider the singly reinforced concrete beams. Singly reinforced concrete beams have the steel in the tension side only, and in only one side only. Now, let us look at first the rectangular section as shown here in the figure. The rectangular section has a width of B. Overall depth of the beam is capital D. And it has reinforcement as shown here. The area of reinforcement is AST. So the area of reinforcement here is AST in tension. And the depth from the topmost compression fiber in concrete to the centroid of the steel is given by small d, is denoted by small d, and which is called as effective depth. Now, this concrete beam is subjected to the 4-point loading as shown in the figure. So there are two point loading acting as shown in the figure here. So if we draw the bending moment diagram, the bending moment diagram will look like this, and the shear force diagram we know will look like this as well. Now, for this cross section with this area of reinforcement, the reinforcement ratio rho is given by the area of steel AST divided by the area up to the centroid of the reinforcement, that is this one. That means B multiplied by effective depth D. So AST divided by the area up to the centroid of the reinforcement is called as reinforcement ratio. So now Once we know these parameters, we can now analyze this reinforced concrete beam. If we start applying the load to this reinforced concrete beam and take a cross section at the midspan of this beam, we see the stress strain profile like this one when the load is very small. At the very small load level, the strain and the stress profile both are linear as shown in the figure here. Now, if you look into the strain profile for this cross section at the midspan of the beam, it is linear as shown here. Epsilon C here denotes the strain at the topmost fiber in the concrete beam, which is in compression, and the bottom part is in tension. So epsilon CT is the tensile strain in concrete at the bottommost fiber here, and epsilon CT denotes the strain in the steel at this point. And we assume that the steel is perfectly bound with the concrete, so the strain at the same point where this steel is same. The strain in the concrete and the steel are same at the same point. Now, if we look into the stress profile, sigma C denotes the compressive stress at the topmost fiber, and sigma CT denotes the tensile stress in the concrete at the bottommost fiber. And as you can see, the stress profile is still linear for this beam. And the depth of the neutral axis, where the stress is 0, is denoted by dn. Here, dn, the depth of neutral axis, can be written in terms of effective depth by multiplying it with Ku, where Ku is the neutral axis depth parameter. So at this very low load level, the distribution of stress and strain are linear, and strain of concrete and steel at the same position are the same as I discussed earlier. The relation between the moment and deformation is still linear, and the stress in steel is extremely small at that point, and hence we neglect the stress in the steel at that point. And we can compute the moment, bending moment at this point, using the Flexure formula. So the bending moment M can be written as sigma CT, that is the tensile stress at the bottommost fiber, multiplied by the section modulus Z. So for the rectangular section modulus can be written as BD square by 6, where Z is equals to the modulus moment of inertia of the beam divided by d by 2, and that's where we get BD square over 6. Now, if we further increase the load for this beam, the strain and the stress will increase as well. And as you can see, the strain in the steel and concrete has also increased, and also the stress will keep on increasing as well. And at a certain point, the tensile stress in the steel at the bottommost fiber will increase and reach the tensile strength of the concrete, which is denoted by F-CTF. So the bottommost fiber, the tensile stress in the concrete will reach the tensile strength of the concrete. And at that point, when the stress is equal to the tensile strength of the concrete will start to crack at the maximum bending moment region. Now, when the concrete starts to crack, the steel will start to take the tensile stresses. As you can see here, the steel is now taking the tensile stresses now. So at this point where the concrete starts to crack, the moment is called as the cracking moment. The moment that causes the concrete to crack is called as cracking moment, and it is denoted by MCR. So when the tensile stresses of concrete reaches the flexural tensile strength of the concrete, F-CT.F, flexural cracks will appear at the extreme tension fiber, and the steel starts to take tensile stresses now. Now at this point, the cracking moment is given by, the cracking moment is denoted by MCR, and using the flexural formula again, it can be computed by the stress at the extreme tension fiber multiplied by the section modulus, and we know that when the concrete will start to crack, FCT is sigma CT is equal to the tensile strength of the concrete multiplied by the section modulus. So we know the tensile strength of the concrete and we know the section modulus of the given beam, so we can find the cracking moment for the beam here. So jet is still taken as PD square over 6. Now, if we further increase the load, the crack will start to appear, more cracks will start to appear in the beam in the maximum moment region, and the cracks will also enlarge as well. And another thing that we'll start to see is that all of the tensile stress will now be taken by the steel. As you can see, all of the tensile stress is now taken by the steel only, and we neglect any tensile stresses taken by the concrete below the neutral axis. So the concrete is now taking only the compressive stress and the steel is taking all the tensile stresses. And also another point to note here is that the stress profile in the concrete will start to become non-linear. As you can see, the stress in concrete is becoming non-linear here. Now, if we integrate the volume under this stress curve, it gives the total compressive force acting in the concrete. So that gives the total compressive force acting on the concrete here, that is denoted by C. So if we integrate the total volume under the curve, that gives us the total compressive force acting on this block, compressive block of concrete. And T denotes the total tensile force acting on the steel. So the total tensile force can be computed by the area of steel, which is AST, multiplied by the stress in the steel, that is sigma ST. So that gives us the total tensile force that is acting on the concrete, whereas the total tensile force acting on the steel, whereas C denotes the total compressive force acting on the concrete. So now for the horizontal equilibrium of these forces, the tensile force has to be equal to the compressive force, and the bending moment can be computed by taking the moment about points T, point of application of T or point of application of C. So the bending moment M, external moment M, should be equal to C multiplied by Z or T multiplied by Z. Here Z denotes the distance between the compressive force and the tensile force, and it is called as lever arm. So with that we can find out the moment acting on the section there. Now if we further increase the load, the strain and the stress in this concrete and steel will further increase, and at some point the strain in the concrete will reach 0.003. That is, the compressive strain at the extreme compression fiber will reach 0.003. That is a crushing strain of concrete, and that point the concrete in the compression side, extreme compression side, will start to crush at this point. So this is the point where we consider that the beam has failed. At this point the steel strain is at epsilon ST, and the steel stress is sigma ST as shown before, and again the stress profile in the concrete is nonlinear as shown here. and the moment at this stage is called as the flexural ultimate moment capacity of the beam. Now we can find out the strain in the steel at this failure point by using the strain compatibility equation, and it is strain compatibility equation can be derived using a similar triangle equation between this triangle and this triangle. So if we use a similar triangle equation, epsilon st divided by this distance, which is d minus kud, should be equal to epsilon cu this divided by kud. So which implies the strain in the steel is equal to 0.003, which is the crushing strain of the steel concrete, multiplied by so we're using the strain compatibility equation. We can find out the strain in the steel at the failure load, and here Ku is again the neutral axis depth parameter, where Ku is equal to the ratio of the neutral axis and depth dn divided by the effective depth d. As discussed earlier, if we integrate the volume under this stress curve, stress profile in compression, stress profile in concrete, it gives us the total compressive force that is acting on the concrete. Now it's rather difficult to integrate the volume under the nonlinear curve here. So instead of integrating the volume under this nonlinear curve, we will simplify it, we will idealize it, the nonlinear true stress block with the equivalent rectangular stress block as shown here. So what we do is, instead of this true stress curve, we will simplify it as a rectangular stress block as shown here, and the width of the rectangular stress block is defined in the AS3600 as alpha 2 fc dash, and the height of the stress block is defined as gamma kud, where alpha 2 and gamma are constants given in the code. So we can find out what is the height and the width of the stress block, and so we can easily find out the volume of the block as well. And so the volume of the block is equal to C, that is the total compressive force acting in the concrete. So the nonlinear regular shape stress block is idealized as the equivalent rectangular stress block in such a way that the volume under the rectangular equivalent stress block is equal to the volume under the true stress block. And also the point of application of the compressive force C is at the same height from the neutral axis as well, so it is at the same height as well. So we can simplify the true stress block using equivalent stress block, where alpha 2 and gamma constants are given in the code. So as you can see in AS3600, now we are only looking at the compressive side of the strain and the stress profile. As you can see, this concrete has just crossed, that is the compressive strain in concrete is 0.003, and the true stress block represented by the nonlinear stress profile here, and the compressive force is acting at the distance of gamma kud over 2. Now we are representing this true stress block using an equivalent rectangular stress block in such a way that the width of the equivalent rectangular stress block is alpha 2 fc dash, and the height of the equivalent stress block is gamma kud. So the point of application of C is gamma kud over 2. So again, as I discussed earlier, alpha 2 and gamma are constants, and which are given in AS3600. So if you look into AS3600 clause 8.1.3, it gives us the equation to find out alpha 2 and gamma to draw the equivalent stress block. As you can see, alpha 2 is given by this equation and gamma is given by equation 8.1.32. And the maximum value of alpha 2 and now we know that the neutral axis depth ratio, as you can see again, is given by, as we discussed earlier, is given by Ku is the ratio of the neutral axis depth dn over the effective depth d. So now as we idealize or simplify the true stress block using an equivalent rectangular block, we can easily find the volume of this equivalent stress block to find the total compressive force C. So the resultant compressive force in the concrete is represented by C again, which is the volume of the equivalent rectangular block here. So the to find the area of that, it is alpha 2 FC dash multiplied by the height, that is gamma KUD, multiplied by the width of the beam, that is B. Now why the width of the beam? Because if we look at the cross section of the beam here in 3D, and the neutral axis depth is somewhere here, so your equivalent block is like this. So we are trying to find the volume of this equivalent stress block, and that will give us the total compressive force acting in the concrete C. So we have to multiply the width of the beam as well, which is denoted by B here. So the total compressive force acting in the concrete block can easily be found using this equation now. And this compressive force will be acting at gamma KUD over 2. So the point of application of the compressive force is gamma KUD over 2. So now we know all the parameters in this equation to find the compressive force acting in the concrete block except for Ku. So we don't know what is Ku. Apart from that, we know alpha 2, as we can find out from the equation. Gamma we can find out from the equation as well. Fc dash is the strength of the concrete, which we already know. D is the effective depth from the cross section, we can find out. B is the width of the beam, which we already know. So the only unknown parameter is Ku. So we need to find Ku to find the compressive force acting in the concrete. Now to find the Ku parameter, that is the neutral axis depth parameter, we have to assume the type of failure of the concrete beam, and then we will find Ku, and then we will check that. So to look into that, we have to consider what kind of failure the beam can have. So let's look into the different kinds of failure the rectangular reinforced concrete beam can have. So there are 3 different kinds of failure that the reinforced concrete beam can have in flexure. So the first type of failure is called as tension failure. This type of failure occurs in the under reinforced section. So the sequence of this failure pattern is that first the steel at the bottom in the tension will start to yield. That means epsilon st, the strain in the steel, will be greater than epsilon sy. The steel will yield first, and as we process, as we increase the load, the concrete will finally, in the compressor, finally reaches the crushing strain, that is 0.003. And at that point, we consider that the beam has failed. So the sequence of failure here is that first the steel will yield, and then second the concrete will crush in compression. And this kind of failure is called as tension failure or under reinforced failure. This failure is ductile failure or more desirable kind of failure mode. Now, now if we look into, So now if you look into the stress strain curve of steel, so that is epsilon st, and this is the stress in steel sigma st. So we know that it is bilinear, and in the tension failure mode, the steel will yield first before the concrete crushes. So the steel is somewhere here. That means the strain in steel is already greater than the yield strain in the steel. As you know, the yield strain in steel is epsilon sy, which is equal to 0.0025. Now at the point of failure, the steel has already yielded, so the steel in strain is greater than 0.0025. So now the corresponding stress in the steel, so it is a little bit offset here. So if we draw here, the corresponding stress in steel, as you can see here, is Fsy. That is, when the strain in steel is greater than 0.0025, when the strain in the steel is greater than Fsy, the stress in the steel is equal to the yield strength of the steel. Now in Australia it is 500 megapascal. So looking at this point, if we go back here, we see that when the strain in the steel is already greater than 0.0025, the stress in the steel is equal to the tensile strength of the steel, that is Fsy, which is equal to 500 megapascal. And the equivalent stress block is exactly like before, and once we integrate the volume of this equivalent stress block, that will give us the total compressive force, and the total tensile force T is equal to the area of steel multiplied by sigma st, and in this case area of steel is AST and sigma st is equal to Fsy, so we can write Fsy here, and and Fsy is already known. We know that Fsy, that is the tensile strength of steel, is 500 megapascal. The yield strength of steel is 500 megapascal. Now we can compute C, the compressive force, exactly like the equation before, of by finding the volume of the equivalent stress block like we did before, and the tensile force in the steel is AST multiplied by Fsy when the tensile strain in the steel is greater than epsilon sy. The tensile stress in steel is equal to the yield strength of the steel. So now for the horizontal equilibrium of the forces, compressive force has to be equal to the tensile force T. So as we know the diagram before, C is acting here, the tensile force is acting here. The distance between C and T is denoted by the lever arm jet, which is equal to D minus gamma Ku D over 2, because the point of application of C is gamma Ku D over 2, and the depth of the steel is D. So now if we write down the equation of C, that is alpha 2 should be equal to the area of steel, and as the steel is already yielding, we can write the yield strength of the steel Fsy. Now solving this equation, we can find what is Ku, or neutral axis depth parameter Ku, equal to so this equation we can use to find the neutral axis depth parameter. Can be calculated using this parameter. Once the neutral axis depth is known, we can easily find the the ultimate bending moment capacity or the nominal bending moment capacity by taking the moment about point C. So if we take the moment about point C here, the nominal moment capacity or the ultimate moment capacity, mu equal to the tensile force in the steel T multiplied by the lever arm Z here. So T is nothing but area of steel, and it is already yielding, which is Fsy, and lever arm is here. Fsy is 500 megapascal, because we know that the yield strength of steel is 500 megapascal for Australia. So with this equation, we can find out the ultimate moment capacity of this rectangular beam when it is failing in the tension mode. And as I mentioned before, the tension failure is ductile failure and a desirable kind of failure, because the steel yields in this one and the beam fails, beam crushes second. As you can see in this figure, this is a tension failure, typical tension failure. As you can see, as we keep on loading the steel here, steel is in tension side, it started yielding, and finally the concrete crushed here. Steel had already yielded, and then finally the concrete crust. Now if you notice here, there are so many cracks happening in the tension region here, and you can see that there is a the concrete beam has it has gone through a large deformation, but still it is holding intact. That means the beam hasn't completely collapsed, but it is still intact. So this is the kind of failure that we want. So that means, what it means is that it is a ductile failure. We can see a large deformation before the beam will actually fail. We will see a large deformation before the beam fails. So, and that is a desirable kind of failure from ductility perspective. Now this is the practical that we did in CS 3001, and if we can see, hopefully it will play, we'll see how ductile failure looks like. So as we keep on increasing the load, we see that the cracks are starting to happen in the concrete beam in the maximum moment region, and the cracks starting to get bigger, and perhaps the steel has starting to yield at some point, and we can see that the cracks are getting pretty big at this point here, and finally the concrete is starting to crush here, right? And the beam is considered to fail when the concrete crushes in the compression region. So again, as I said before, it is a very ductile kind of failure. Even though the concrete has the beam has failed, it is still intact. That means the beam hasn't collapsed yet. And from the structural safety perspective, it is a desirable kind of failure, because that will give occupants to run for safety before the beam collapses. So it is a very ductile kind of failure. Now in this beam, once it collapsed, we remove the steel, and we look into the steel after the beam collapsed, and we saw that, as you can see here, the steel in the tension side, you can see a clear necking here. That means the steel was already yielding before the concrete crushed. That means the steel yielded first, and then the concrete started crushing, which is the typical behavior of the tension or under reinforced sections. So that is one typical kind of failure, that is a tension failure, where the steel will yield first, and then the concrete will reach the compressive strain, that is 0.003, and the beam is considered to be failed. Now the second kind of failure is compression failure, which happens in over reinforced section, when you have large amount of reinforcement in the beam. The reinforcement is the area of reinforcement is pretty high, so it cannot yield. So the concrete will crush first before the steel will yield. So the typical nature of the compression failure is that the steel strain is still less than epsilon sy. That means steel hasn't yielded yet, but the concrete will crush first. compared to the tension failure. In the tension failure, the steel will yield first and the concrete will cross. But in the compression failure, the steel hasn't yielded yet, but the concrete will crush first and the beam is considered to fail. Now, if we look into the stress strain curve of steel again, so again, looking at the stress strain curve of the steel, so in the compression failure mode, the steel hasn't yielded yet, so it is somewhere here. So the yield strain of the steel is epsilon sy, but in our case the steel hasn't yielded yet, so epsilon st is somewhere here and the concrete has already crossed. So you see that the steel stress is sigma st, which is smaller than the yield strength of the steel. So steel hasn't yielded yet, so the stress in the steel is not equal to or less than Fsy. So it is not equal to Fsy. In fact, sigma st is less than Fsy because steel hasn't yielded yet and it is less than epsilon sy. So that is a typical behavior of the compression failure mode. So in this case, as I said, the steel strain is less than epsilon y. That means the stress in the steel sigma st is still less than Fsy. It hasn't yielded yet. But again, other things remaining same. The equivalent stress block is still given by alpha to Fc dash and gamma KUD, and the point of application of compressive force is still given by gamma KUD over 2, and the lever arm between C and T is still denoted by Z. Now, so as you can see in this figure, this is a video from YouTube, and as you can see in this in this picture, the steel hasn't yielded yet, and there are no cracks, visible cracks yet, but the concrete has already crossed and the beam has failed. So the typical idea of this compression failure is that the beam will fail without any cracks or any deformation, large deformation. So it is a very brittle kind of failure. Without any warning, the beam will suddenly crush in compression and will fail. Let's look at the video here.
This video shows an over-reinforced concrete beam being tested in bending. The specimen is made from concrete containing regular Portland cement. The rebar is regular reinforcing steel. The loading diagram shows the beam being subject to 4-point bending. The testing rig is now starting to apply vertical loads to the specimen. We can see the beam displacing and cracks opening up on the tension side of the beam as expected. Then all of a sudden, the concrete in the top surface of the beam fails explosively. Right, let's slow down the footage. Let's look at the top surface. Remember that the top side of the beam is under compression. Because we have heavily reinforced the lower part of the beam, which allows a large amount of tension to be carried, the same large amount of compression needs to be carried by the concrete near the top. This causes the concrete to crush before the steel has a chance to yield. Now, for a structural engineer, that's a bad way for a beam to fail, because concrete crushing is brittle, it's sudden, and you don't get the gradual failure that you'd obtain in an under-reinforced beam. The graph shows an initial linear relationship between the applied load and the vertical displacement at midspan. Note that there is no plateauing in this plot because the steel doesn't yield. Instead, the rising plot simply stops, which implies a sudden failure, just as we saw in the video.
Now that shows how the compression failure beam will look like at the point of failure. So it is a very brittle kind of failure, as we saw in the video, and it is not a desirable kind of failure. Now to analyze a over reinforced section, that means the compression failure mode. So again, we have to compute the compression force C and tensile force T in that equation. And if we just draw the force profile here, so we know that the compressive force is acting here in the concrete, and the tensile force acting on the T, and the lever arm is Z. So the compressive force is given by the volume of the equivalent stress block, that is alpha to FC dash gamma KUD multiplied by B. So that gives the total compressive force in the concrete, and the tensile force in the steel is given by the area of steel multiplied by the stress in the steel. Now please note that the stress in the steel, we do not know it yet, because it is it is not equal to FSY, so we do not know it yet. So sigma ST is less than FSY somewhere, so we do not know exactly what it is. So what we can do is we can write sigma ST in terms of the strain in the steel using the Hooke's law. So Hooke's law says that the stress is equal to the strain multiplied by the Young's modulus of the steel, ES. So writing it again, so it is equal to ES. So now that means the strain in the steel can also be written in terms of the strain in the concrete using the strain compatibility equation, as we said before. So the strain in the steel can be written as epsilon Cu, that is equal to the tensile the compressive strain in concrete, which is 0.003 multiplied by 1 minus Ku over Ku. So now that this is equivalent to epsilon St using the strain compatibility equation. Now we know that epsilon Cu is 0.003, and so we can compute it in terms of Ku here. So for the equilibrium of forces, C has to be equal to T as written before, and that means alpha 2 Fc dash gamma KUdB should be equal to (1 minus Ku over Ku). Now this equation is quadratic in Ku, so if we solve, everything else is known except Ku, so we can solve this equation for quadratic equation for Ku and find the value of Ku. So once the Ku is known, we can find the ultimate moment capacity by taking moment about point C as we did before. So if once we know Ku, solve for Ku by solving the quadratic equation. So once we know Ku, the ultimate moment capacity for this over reinforced beam or in the compression failure mode is if we take moment about point C, T multiplied by Z, the area of reinforcement multiplied by sigma St, which is the stress in the steel, multiplied by so with this we can find out the ultimate moment capacity of the section, because we can express sigma St again in terms of the strain in the concrete, and we can find that out as well. So in this way, for the compression failure mode, if the beam is failing in compression failure mode, we can find out the ultimate moment capacity. Now the third kind of failure is called as balance failure mode. In the balance failure mode, the concrete and steel reaches its ultimate strain simultaneously. What it means is that the strain in the steel reaches epsilon sy, that is the strain will and the steel will start to yield, and at the same time the concrete will start to crush, meaning it reaches the compressive strain, crushing strain in the concrete, that is 0.003. So the steel yielding and the concrete crushing will happen at exactly the same time. So at this point epsilon st is equal to epsilon sy, and remember epsilon sy is 0.0025 if we are using 500 megapascal yield strength steel. Now because the steel is yielding at that point, remember the stress strain curve of steel again. Bilinear stress strain curve. When the strain in the steel is yield strain, the corresponding stress in steel is Fsy. So we can write Fsy here, which is equal to 500 megapascal. Now, because we know all the parameters, we can straight away find the effective, the neutral axis depth for the balance failure mode using the strain compatibility equation. So from the strain compatibility equation, using the similar triangles like we did before, we can find out, because the strain in steel is already reaching at the yield strain, so we can write it as epsilon sy divided by this depth, which is d minus ku. Now because it is a balance failure mode, we'll write ku as kub d should be equal to the strain in this concrete, that is the crushing strain 0.003 divided by this depth, which is kubd. Now that implies that we can we know the yielding of this concrete steel will happen at 0.0025, and we know that yielding of the concrete will the crushing of the concrete will happen at 0.003. so we can find out the neutral axis depth parameter kub for the balance mode failure mode as just rearranging the equation. We can find it out epsilon cu divided by epsilon sy, where epsilon cu is the crushing strain of the concrete, which is given by 0.003 plus the yield strain in the steel is 0.0025. So the neutral axis depth parameter kub for the rectangular section with 500 megapascal steel is, if we can do the calculation here, we'll see kub is 0.545. So for the balance failure, the neutral axis depth parameter kub is 0.545. So once you know the ku, we can easily find the ultimate moment capacity for the balance section as well. So as you can see here, at the balance point, the ultimate moment capacity MUB is again similarly the tensile force multiplied by Z. This is the tensile force T, and the Z is the lever arm here. So this represents the jet. So again, writing it in a different way. This is the tensile force T, and this parameter represents the lever arm Z here. Now for the force equilibrium, of the forces, C has to be equal to T. So again, equating the forces, alpha to Fc dash should be equal to area of steel multiplied by the yield strength of the steel. So all of the parameter KUB is also known, so we can find out AST. The area of the steel for the balance failure is equal to So we can find out the area of steel that will give the balance failure mode. So we can find out the area of steel for the balance failure mode, and correspondingly we can also find the reinforcement ratio for the balance section. That means the reinforcement ratio, as we know, is the area of steel divided by BD, where B is the width of the beam and D is the effective depth of the beam. So if we divide this by BD, we get KUB is the neutral axis depth parameter for the balance section. So rho B, that means the reinforcement ratio for the balance section is given by this equation. So what this equation does is that we can find out what amount of steel in the concrete beam will give the balance section. So any steel more than the balance section will go into the over reinforced region, and any steel below the balance section goes into the under reinforced region. So the next slide will make this one a bit clearer. So there are three different kinds of failure, as we said. If the reinforcement ratio rho is less than the balance reinforcement ratio rho B, or also the neutral axis depth parameter KU is less than KUB, where KUB is 0.545, then we have the tension failure mode, or the under reinforced failure, which is a ductile desirable failure. Now if the reinforcement ratio rho is greater than the reinforcement ratio for the balance section, that means the neutral axis depth is greater than the neutral axis depth for the balance section, which is 0.545, we will go into the compression failure mode, which is a brittle, non-desirable kind of failure. So the neutral axis depth will look like this one. For the ductile behavior, neutral axis depth looks something like this one. So when we are designing a beam, we want KU, the neutral axis depth parameter, to be between 0.15 to 0.3 to make it really a ductile beam. You know that 0.545 is the boundary where it goes into the compression brittle failure mode, but we don't want to get to the 0.545 even. We want KU to be smaller and be in the range of 0.15 to 0.3 only. It will be a ductile failure. And if the KU, or the neutral axis depth parameter, is greater than 0.45, it really goes into the brittle failure mode. So to achieve a under reinforced or tension failure mode, which is a ductile kind of failure, the reinforcement ratio in the beam is kept in the range of 0.01 to 0.02. So the reinforcement ratio, if it is between 0.01 to 0.02, we know that it will go into a tension failure or under reinforced ductile failure. If it is greater than 0.45 or 0.36, if it is greater than 0.36, it really goes into the non-ductile region, and we don't want to go into the brittle failure. And the corresponding range of KU for the ductile failure is 0.15 to 0.3. So KU, if KU is between 0.15 to 0.3, it is ductile failure, and if the KU is greater than 0.36, it becomes brittle failure. So we want to avoid KU greater than 0.36 when you are designing a reinforced concrete beam. So now let's look into the strain profile for all these three different kinds of failure. First one, for the tension failure, as you can see, the under reinforced failure. So when the beam has lower amount of steel, so it doesn't have too much steel, it has a lower amount of steel as shown here, the failure will be tension failure. So tension failure is characterized by the steel will be yielding first and the concrete will crush. So that means the steel is already yielding, as you can see here. Epsilon ST is already greater than epsilon SY, and then the concrete will crush. So for the under reinforced failure, the reinforcement ratio is less than the balanced reinforcement ratio, and the neutral axis depth KU is also less than 0.545, which is the neutral axis depth parameter for the balance failure. Now let's look at the over reinforced failure. As you can see, in the over reinforced failure, we have too many reinforcement in the tension side, so the steel cannot yield and the concrete will crush fast. So the strain profile will look like represented by this red line. So as you can see here, the steel has not yielded yet. Epsilon ST is still less than epsilon SY, but the concrete has crushed at this point. Now for the over reinforced section, as you can see, the steel has not yielded. The reinforcement ratio is greater than the reinforcement ratio for the balance section, and the neutral axis depth parameter is also bigger than the balance section as well. Now the third failure mode is the balance failure, where the reinforcement is in between the under reinforced section and the over reinforced section. For the balance failure, as we discussed earlier, the steel will just start to yield and the concrete will cross at the same point, and the reinforcement ratio is denoted by rho b, and the neutral axis depth parameter is denoted by KUB for the balance failure. Even though the balance failure sounds like a good kind of failure, but it is still a brittle kind of failure, and we don't want the beam to fail in the balance failure or the over reinforced failure. So we want the beam to fail in the under reinforced failure, giving a ductile behavior. So if you look into the moment curvature curve for tension failure, compression failure, and the balance failure, it looks like this one. So the beam A, if it is an under reinforced failure or the tension failure, as you can see, it is a very ductile kind of failure. The steel will start to yield at this point, and it is a very ductile failure, whereas the balance failure and the compression failure is a very brittle failure. Yes, it has a higher moment capacity compared to the under reinforced failure, but once it reaches its ultimate moment capacity, it just fails, unlike beam A. So from the structural safety perspective, we prefer beam A because it is behaving ductile in a ductile manner, whereas beam B and beam C have a very brittle, abrupt kind of failure, even though the moment capacity is higher. So we don't want beam B and beam C in our structural design. We want the beams to behave in a tension failure, as we can see here.